Just a minute. Okay, sorry about that. Good morning, everyone. So today we will continue to talk about the EMF, and in particular, we will talk about motion on EMF and relates that to Faraday's law. So previously in our class, we have talked about the EMF is defined to be the line integral of this force per unit charge. This force is what is driving the current in the circuit. So if we, for example, if we look at a particular circuit light looks like this from point A to B, and if we have a resistor in there, and there's a current running through the circuit, so we can derive the EMF for such a circuit. We can see that within the battery, we can do this line integral for two parts. One is inside the battery, one is outside of the battery. So inside battery, this is your positive plate, this is your negative plate, right? So your E field is pointing from your positive plate to the negative plate. And there is also another force, that is force of the battery, that's pointing in the opposite direction of the battery. Outside of the battery, there is no force from the battery, of course, and outside of the battery, you only have the E field. And also, because this is a steady current, charges, which means the charges are not accelerating. Okay. Because of this, we know that for the charges inside the battery, they must have a net force of 0, because they have a steady current. So because of that, you can relate E and force of the battery together. Is that, okay, this is force per unit. The force from the E field is QE, right? The force from the battery is QF of the battery. Because the net force is 0, then you can say the E plus F of the battery must be 0. Okay. Okay, so we'll go back to derive this EMF. So when we do the line integral, right, from point A, go from A to B, right, and then from B to A. That's go all the way around from A to B and then from B to A. Okay, from A to B, the total force would be the force of the battery plus the E, the L. From outside, the only force is the E field that's acting on the charges. So that's E dot into dl. And we had just derived within the battery, these two are add up to be 0 because the charges are not accelerating. So this is 0. Then the EMF is really just going to be B to A, E dl. From B to A, we can rewrite that using negative from A to B, E dl. And we're very familiar with this definition, right? Negative from A to B, E dl is really the delta V, the potential between A and B, right? This is the potential VB minus VA, which is exactly the voltage of the battery. So we can see from this little derivation that the function of having such a battery is for us to establish and maintain the voltage difference across the two ends, and the voltage difference is equal to the little f, the EMF, the electromotive force. That's another further showing the physical meaning of EMF is really the voltage across the battery. Okay, so this is showing voltage across the two ends of the battery is the electromotive force. You can see that here, what is driving the current is the battery. You have a chemical reaction going on. And there's also another way to drive a current is through something we call motional EMF. It has to do with motion of a metal moving inside a magnetic field. So now let's talk about the motional EMF. To start with, some magnetic field in space. So let's say we have a magnetic field in this region that's pointing into the page, and I have a metal bar that is moving to the right with velocity v. And the length of the bar is L, for example. Okay, so inside these metal bar, there are all these charges, right? And we know that if you have a charge Q moving inside a magnetic field with some velocity, then there will be a force acting on the Q. Do you still remember how to calculate this force? The force is Q V
Cross B.
Cross B. Very good. All right. So of course, these are electrons, right? Which means the Q is negative E. But just for the sake of arguing, we're just treating these are positive charges that are moving. But you know, in real life, it's negative charges are moving in the opposite direction of where the positive charge would have been moving. But let's just say you have all these little charges inside the bar and they're moving. And it's going to feel a force that's in the direction of V cross B. Now you could write this F as the force per unit charge, which is F over Q. Then you can just worry about the V cross B. Okay, so do the right-hand rule. In which way is V cross B? Which direction is it going to point? V is pointing to the right and B is down. So this force is pointing upward, right? So this force is going to point upward, which means these positive charges are going to accumulate on the top end of the bar. Now, the negative will be accumulating on the other end of the bar, of the metal bar, right? So what does that give you? If you have a top positive charge and negative charges are separated by distance, yes, and what would that create in between them?
An E field within your material.
E field, and also we can say there is a potential difference, right? Within the ball. So now it's like this is just like a battery. You have a positive and the negative end. It's like a battery. So like draw a little battery here. Okay, so it looks like a battery. You have an EMF created due to the motion, and we call these kind of this kind of EMF the motional EMF. It has to do with the movement of the metal. Okay, so this creates an EMF. Creating a potential difference. If you have, let's say, the B field, again into the page, and I'm going to complete this into a complete circuit. So if I have one metal bar here, and I have another metal bar here, connected by wire, and you can ignore the wire, just the metal bars. So if we look at the motion of the two metal bars, each of them will become like a battery. So this one will become like a battery, this become like a battery because they're moving in the same way. So is there going to be any current inside the circuit? If I have one battery like this connected to another battery like this, is there going to be any current in here?
I would argue no.
No, right, because when we connect our batteries is in this way is negative, positive, negative to positive, right? But not positive, positive to connect it. So this one actually will give you no current because the two EMF cancels from the two sides. So EMF is 0. However, if you really just have one metal bar and you create a complete circuit, then you're going to have some EMF. So say I have one metal bar here, and it's this complete circuit is now leaving the B field area. So let's say B field ends right here, and part of the circuit is in the B field, part of the circuit is outside of it, and it's continuing to move in this direction, right? This metal bar is moving. So we can find out in which way the current is going to be flowing. All right. Okay, so this is L, and current, this is positive, this is negative, right? Positive, negative. So it's going to drive a current flowing in this direction if you have a complete circuit. If you don't have complete circuit, it's like it will become a battery, but if you don't connect the battery with a wire, it will not have any current. So this one does have current. The EMF is F dot into DL. F is V cross B. So V cross B dot into DL, V and B are perpendicular, so this one just becomes V times B. And the entire length that we are integrating over is the length of this metal bar, which is L. So the EMF is V times B times L. This is something from the intro physics you probably still recall, right? ELV is the emotional EMF generated inside the magnetic field if you're moving perpendicular to the B field. Okay, so this is V times B times L. And you do not have to worry about this top and the bottom leg. And you do not have to worry about this leg because this leg has no B field, it's outside of the B field, right? Side of B. So it's not going to generate any EMF. And the top and the bottom leg, the F is perpendicular to the L so that you're not going to create any potential difference. So what is our F? Our F is pointing up the page. Okay, that is our F. And DL is along the length of my integral. So on the top leg, my DL is to the right. So these two are perpendicular. It's not going to give me any dot product. So this one is just for your left leg, and that's the only contribution, right? The other two, top and bottom is 0. Right leg is also 0. Right leg. So EMF is B times L times V. Further, we can calculate the current produced in this. So if we want to know the current, this is the delta V, then current will be delta V over resistance of the entire circuit. So you just need BLV divided by what delta R of the loop, sorry, the resistance of the loop, and you can get the current. Okay, so that's motional EMF. This is a very regular shape. We have a square that is easy to calculate. However, sometimes when your shape of the loop is a little more difficult to calculate, we have another way to do this. So we're looking at a magnetic flux instead of looking at motional EMF. Okay, so now let's look at another way to calculate motional EMF. The way we did right here is look at the force generated by QV cross B. And another way to look at this is if your, in case where your shape is very complicated, or if your B field is not a constant, then this F dot into DL would be hard to calculate using this way. So we're going to look at a different way to look at the magnetic flux through the loop. Okay, so we're going to use the same example as we did before. And we're going to look at a complete circuit, which is now leaving the magnetic field. going to set the origin, let's say right here, and the length of the metal bar is L, just like before. And the distance from the left end to the origin right now is X. I'm going to set up my positive X and positive Y in this direction. Okay, so by looking at the magnetic flux, you can see that, okay, what is the flux through this area? You see flux of the B is B dA, right? And B is a constant in this case. And the area is one side multiplied by the other side, which is L times the magnitude of X. So that's area. And if we are looking at the change of the flux over time, in this case, my B is a constant. The only thing that's changing the flux is the length X. As you move further away, you can see you have smaller and smaller area immersed in the B field. So if I were to draw a next moment, when you're moving, let's say after 5 seconds, you have moved over here, you can see the area immersed in the B field is now smaller, right? So because X is decreasing with time, so dx dt. So because V is pointing to the positive direction and dx is decreasing, so X is decreasing, which means dx dt is smaller than 0. So if you do dx dt, is going to be what? Negative V, right? Negative V, velocity. So you can see the change of flux over time is negative V times L times V, which is exactly what we derived earlier, VLV. So it seems like the EMF can also be calculated by the negative d flux over dt, the change of flux over time. This is the EMF. So we calculate the same scenario 2 ways. One way we do it viewing as emotional EMF. Another way we view it as the change of flux over time. And it turns out, this is what we later on will talk about, is the Faraday's law. Sometimes you don't even have to have motion. As long as you have a change in flux, you can generate the emotional EMF. You can generate an EMF. We just won't call it emotional EMF when it's not moving. And we will talk a little bit more about the negative signs later on. Right now, we're just gonna leave it as it is. The negative sign has a very significant meaning, physical meaning, but we'll wait for a little while. Okay, so it turns out you can also calculate your EMF this way, as a change of flux over time. All right, now let's look at a couple of questions. So we have just done an example together where you have a metal loop leaving the field. Now you have a metal loop entering the B field. So which way do you think the current will flow? You could do it as emotional EMF way, or you can think of the in terms of the magnetic flux. Either way, if you still remember how we did the Faraday's law in our intro physics, if you don't remember that, you can simply look at the emotional EMF method. Okay, all right, I'll let you have a discussion about this question. It shouldn't take too long, maybe a minute or 2 on this question, and after you are come back, we can have a discussion. 1 second. Okay, 10 more seconds on this question. Okay, any last minute vote? All right, I'm gonna go ahead and close this. All right, so majority voted for clockwise, and they're a little bit voting for counterclockwise or no. So we're sure that there is going to be an EMF, right? There was one before, and this one looks just like the other one. Is part of the loop is out of the B field and part of loop is in. As long as they're not both in. Now, if you're both in, then it's like you have two batteries connected and they cancel their EMF, right? So for sure we will have a current. So how do we figure out the direction? Can you guys let me know the method that you use to figure out the direction of the current?
Well,
I
if you
like to
use,
think of it in terms of conservation of energy.
Okay, yes, go ahead. Can you say
So if we have some changing flux with respect to time, we know that that will induce a current within our closed loop. And Lenz's law tells us that we need to have a B field around this current, which opposes the change in flux. Since we know that our B field is pointing out of the page, we can say that the B field has to move in the opposite direction of the B field coming out of the page, which in this case would be clockwise, or the current would run clockwise, so that your B field is moving against your B field coming out of the page.
Very good. So you were using from what we learned from intro physics, the Lenz law. We will talk more about that later. Lenz law and Faraday's law for sure can answer that, and we will put a pin on that. We're not going to do viewing using the magnetic flux here. But what I really like what you said about conservation of energy. If it weren't that way, there will be a violation of conservation of energy. In the sense that you can see that, okay, there is if the current is flowing clockwise, right? So there would be a force exerted on this leg. So if the force on the current, if you still remember how to do this, is IL cross B. So IL cross B give you a force that is pointing to the left. Okay, and it has to be that way, because if your current is flowing counterclockwise or your current reverse direction, then you will have a force pointing in this direction. So it's like as soon as you give this loop a little bit push, it's going to experience a force that drags it moving even more. And if you drag it to move even more, you generate more EMF, and that drags the loop even more. So it's like if once you get the ball rolling, it's going to continue speeding up and generate more current. And that does violate the idea of conservation of energy. That doesn't seem right. So you can view it using that perspective. Or we can do it looking at the battery, which one is a positive end, which one is a negative end. Earlier, Jennifer, were you going to say something about the direction of the current?
yeah, I was just going to say that I use the right-hand rule, and knowing that the force is acting on a positive charge, and we're using conventional current, we're saying current flows in the clockwise direction, but Sebastian's explanation is really helpful.
So you did the V cross B, right?
Mm-hmm.
A V cross B give you a force on the positive charge was pointing down, which means you have created a potential difference like this. So this is your positive side of the battery. This is the negative side of your battery. So current will flowing out of the positive and flowing back into the negative. So that gives us a clockwise current. Excellent, very good. Both ideas are very excellent. And we'll talk more about Lenz's law later, just not right now. Okay. All right, same question. I think in terms of talking about the violating conservation of energy, I already mentioned the direction of the force. So the direction of force on the loop, right? Not just on the leg. So since I already talked about, let's go through this question together. So this is the current clockwise. So to figure out the force is IL cross B, right? So let's look at the force on all the legs, each of them. So I already talked about I cross B. For the bottom leg is you do it L, I going down, B is up, so force to the left. And what about, is there any force on the left leg?
No, because it's not in your B field yet.
Right, not in the B field, so there's not going to be any force on the left leg. What about the top leg? Is there any force on the top leg? When you do IL cross B.
There should be a force pointing down.
Yes, IL cross B gives me a force down. Now, if you do IL cross B on the bottom leg, you get a force pointing up. So these two actually cancels. And this one doesn't have any force. This is the only one that becomes the net force that's acting on the loop, right? So if it's asking about the force acting on the entire loop, then it has to be pointing to the left. But we know that by analyzing all of these four legs and each of them, then they add up to be to the left. On the topic of the energy, so let's talk a little bit about the force and the energy. I'm going to give it a resistance so we can calculate the energy dissipated in the loop. B field, force to the left. So the emotional EMF generated is B times L times V, and the current generated is epsilon over R, just BLV over resistance R. The magnetic force is I L cross B, right? And here is a uniform B field, so it really just becomes I B times L. On the left leg of the loop that I draw here, which is also the total force acting on the entire loop. If we want to calculate the work done by this external force, think about this. Someone is taking this loop and dragging it to the right. You know that as soon as you generate some current, your loop is going to experience a force that's opposing the direction of the motion. So if you want to maintain this velocity, right, implicitly, it didn't say, but you know that there must be someone holding the loop and moving it to the right. That is the external force. That must be pointing to the left, pointing to the right. And that force and this force has to be equal in magnitude for this to move at a constant velocity, right? So because this move at a constant velocity, we know that F net equals 0, so that your external force that you apply has to equal to this magnetic force that the loop is experiencing from the magnetic field. So your external force is also B times L times I, pointing to the opposite direction, that is to the right. We can calculate the work done by such a force. The work done is force times displacement, right? So force is to the right, your motion is also to the right, V is also to the right. So force is B times L times I, and velocity is V times T. And you can replace this current I by the one that we just calculated, assuming that B is a known quantity and V is a known quantity. So we can replace current by B times L times V divided by resistance. And you can calculate the work done by external force is B squared, L squared, V squared, T over R. Work by external force. Okay, now we are going to view this using a different way, is what is the energy dissipated in the circuit? energy dissipated. How do we calculate energy dissipated in the circuit? We know how to do power. So power times time gives me energy, right? So what is power? So how do we calculate power in the circuit? You still remember how to do power? Given current and resistance, power is, you can either do V times I, remember? Or you can do V squared over R, or you can do I squared times R. Like all of them are giving you the power dissipated in the circuit. How many watts is dissipated per unit time? So I'm going to replace power using I squared times R times T. I already know time, I already know the current. So I'm going to plug in my current. VLV over R is my current squared times RT. And what does this become? This becomes V squared, L squared, V squared. R cancels one of the R on the denominator, becomes R times T. And you notice that this expression and this expression are equal, right? Is it a coincidence that they are equal? That the work done by external force equals to the energy dissipated in the circuit? Or is it something you would say, of course it has to be that way? What would you say? Is this a coincidence?
I don't think so. Thinking of the definition of work, which is the integral of F dot dr.
Mm-hmm. So you are talking about energy conservation. I would say this will be a demonstration of what you just said about this is conservation of energy. You have this energy dissipated in the circuit, meaning that, well, you have generated some energy in the circuit. It's being used by the resistor. Or you can have a light bulb, then it will be used by the light bulb to give out light. In this case, it's being used by the resistance to generate this heat. So where this energy coming from? It has to come from the external work, that is work done by you. You are doing work, you're dragging the loop, and the work done by you is exactly the energy dissipated in the circuit. So this one actually shows conservation of energy. One might think, okay, what about the role of the magnetic field in this case? So doesn't that my energy coming from the magnetic field, but not from the work done by you? Let's put a mental note on that. We'll go back to that question later. Could there be work done by the magnetic field in this case that is giving us the energy in the circuit? But we will go back to answer that question. All right, so I wanted to want us to look at this question. In two situations, you have a loop move to the right with this velocity v, or you can move your magnets. You can move your magnetic field with the same velocity to the left. And you have an ammeter connected, so you can read the current in each of the cases, right? So what would you think the current will be related to each other in these two cases? I'm gonna give you a couple minutes to discuss this question, and when you come back, we can vote. Okay, if you haven't voted already, we'll run the clock for 10 more seconds. All right, let's close this and take a look. All right, so we know that one of them we know how to do. We know how to do one. That's the one we talked about with velocity v. You do v cross b, and you do v cross b. You get a force down, which means that you will have a positive end in here, negative end in here. So this is a battery where your current is flowing this way, right? Counterclockwise. So counterclockwise current give you a positive and angular reading. So for one, we know how to do that I1 larger than 0. So two, you cannot really do it using the motional EMF method. So anybody have any reason of how do we figure out what direction will the current flow for scenario 2 if your magnets are moving? Any possible argument we can use?
I thought about it. I mean, I don't know if I was right, but I chose B because I thought about it like neither of these situations, neither the loop or the magnets are non-inertial reference frames. So like if you're at the reference frame of the magnets, both of the times the loop is moving to the right.
Mm-hmm.
So I just said that they're both equal and positive, moving counterclockwise.
So you're saying the magnets moving to the left should be equivalent to the loop moves to the right, right?
Right.
That's very good. That's a good way to look at this. You sort of like using the view of a relativity that in relativity, these two motions are not really all that different, right? Loop moves to the right and is relatively just like the magnet moving to the left. And all what this is doing is a phase shift, right? And then you can solve the differences between two that they should give you the same physical results. And indeed, B is correct. So Faraday experimented this in 1830s. So he have done a bunch of different experiments. So he has experiments that's like the scenario 1, where clearly you can you're able to explain the sort of the mechanism, if you wish to give a mechanism to all of these currents using the view of motional EMF. But there are very many scenarios where you cannot explain it using emotional EMF. For example, like scenario 2, right? The bar itself is not moving, but the magnets are moving. Or there are scenarios where nothing is moving. You're simply turning the circuit on. Like if B field is controlled by some switch, you can turn it on, turn it off, and that is enough to give you a induced current. So he experimented all of this to be able to consolidate these different type of EMFs and using the Faraday's law to explain all the scenarios. In this case, case 1 is like the motional EMF. You can certainly use motional EMF to explain it. Case 2 is a little bit harder. In this case, what would you say is the force, because your velocity is 0 of the bar. So it cannot be a magnetic force, right? So it turns out you can view scenario 2 using a different reference frame. Because later on when we will talk about the change of magnetic field over time is a curl of E. So when B is changing, so here B is moving to the left, so you can view B is changing. So if B is changing, then it will generate a induced E field. So we can view scenario 2, so in case 1 is the magnetic force is driving the current. In case 2, you can think of this as an electric force is driving the current in this reference frame. So E and B are not really absolute. They can be, they depend on your frame of reference. It can be sort of the two sides of the same coin. But the beauty of Faraday's law is that no matter what your scenario is, you can always view this using the change in magnetic flux to explain this. and that is talked about in Lenz's law. So this negative sign represents the change. If your flux is increasing, then to oppose that change, you need to induce a current to produce a negative of that flux. So flux induced has to be opposite to the flux that is increasing. And another way to oppose the change is your flux is decreasing. So to fight that change, you want to produce a magnetic flux is in the same direction as your original flux. Both of which cases is way to oppose the change. So for example, in this case, you're leaving the magnetic field. So the flux is decreasing. So to oppose that change, you want to produce the same amount of B that is in the same direction to oppose that change. You can see that if your B is pointing up the page, your induced direction has to be current has to be counterclockwise. The same can easily explain scenario 2, right? Your B field is dragged to the left. The effectiveness of that is the area that is immersed in your B field is reducing. Your flux is decreasing. So again, you wanted to induce a current that is in the same direction and produce the same B field as you had before. So both of which will give you a counterclockwise current. So that's how we can use Faraday's law to look at this. So let's write a little bit note on this topic. Faraday postulated a law of nature that the EMF is related to the change in magnetic flux. Right, EMF, as we said earlier, integral of EDL because EMF is a voltage, and it seems to be related to the change in flux. So these two are equal. The change in magnetic flux can be calculated by the B field into flux through some area. So it's integral B dA over dt. And on the left-hand side, I can use Stokes' theorem. I can rewrite my line integral using the curl of B, curl of E dot dA. Because according to Stokes, E dot into dl is equal to the curl of E dot into dA. These are equal. So I can rewrite my left-hand side. So you can see my left-hand side and my right-hand side, both are the integral dot into dA, right? So I can derive a differential format of that equation, which is the curl of E that is equal to dB over dt. So this is Faraday's law. Faraday's law, you can write it using an integral format in this case, or you can write it a differential format, which is like this. The integral format, you can represent the change in flux using the change of E dot into dA. So this is your integral format. This is your differential format. So both of these are Faraday's law. So a lot of times we simply saying, okay, what is Faraday's law is telling you is the change in the B field will produce a E field. So this E is not a electrostatics, it's induced E field. It's induced by a change in magnetic field. Okay, so a change in B will produce an E. That's Faraday's law. The negative sign, very importantly, you have to have a negative sign. The negative sign in here, negative dB dt, has another name called Lenz's law. Simply saying nature wants to fight the change, no matter what the change is. If the change is to increase your B field, then to fight that change, you want to produce a induce an E field that's opposite to the B field. If the change is to decrease your B field, then it's opposing that change is to help out the B field that originally had. So that's simply Lenz's law is really just talking about the negative sign. The overall together is Faraday's law. We'll talk a little bit more about Lenz's law later. We'll have more examples to practice the idea of what do we mean by fighting the change. You can see that these are when we have time dependence. Now is a static, not a static situation. For a static E field, right, this is always 0. You can see that now it's different because we have a time dependence. When you have a changing B field, you have an induced E field. All right. There are many applications of Faraday's law. Now, one of the application is magnetic braking. So let's look at a video to show what we mean by magnetic braking.
I would like to do another demonstration of eddy currents and the resulting magnetic braking that will occur on a pendulum. So what I have here are 2 magnets. Okay, so this is like the North Pole here of this magnet and the South Pole here of this magnet. So there's a fairly uniform field in between here, and these are actually fairly strong magnets. So if I actually put a piece of steel in here, if this were a piece of steel, it would stick and I probably wouldn't be strong enough to pull it apart. But what I have here is a piece of aluminum. Okay, so aluminum is paramagnetic, so it is only weakly magnetized, so it's not really attracted to the magnets. Okay, so I also have 2 other pendulums. Okay, this one has slots in it, and this one, the slots go all the way to the bottom, so there's no connection along the bottom. Okay, and any of these I put in here will freely swing. Okay, so now let's see what happens when I try to swing this one through the magnetic field. Okay, notice how it breaks and stops. Now, if I did the one with the slots, we see it also breaks and stops, not quite as quickly. And finally, the ones with the grooves so that there's no connection on the bottom swings freely. Okay, what is happening is that as this one is swinging into the field, you have a changing magnetic field in this region. So that sets up a resulting current such that the magnetic field generated by the current opposes the increase in magnetic field. So that will be a field in the opposite direction, and that is what's causing the braking. Whereas in this one, where we have these grooves, you can't get the circulating eddy currents because of the disconnection between these regions of the metal, and that's why you don't set up those strong induced magnetic field currents and resulting magnetic fields. Let's see if I can further clarify the eddy currents that will start to occur and the resulting magnetic field due to those eddy currents. So let's say we're sitting in that gap between those 2 magnetic poles, and we're looking, say, from the north to the south pole. So this circle signifies the area of one of the poles, and these X's signify that the magnetic flux density is into the page. Okay, so the aluminum pendulum now is trying to slide in like this. Okay, so as the aluminum pendulum is going in, what we see is that in this area, we have an increasing magnetic field inside the aluminum into the page. So that we know is going to induce a current so that that induced current generates a magnetic field that opposes the increasing field into our aluminum here. So that will be a counterclockwise circulating currents are going to start to set up here. So that's going to generate a magnetic field that's coming out of the page and opposing the increasing field into the page due to the aluminum sliding into the field. And the resulting magnetic.
Okay, so we have just watched a demo of the application of Faraday's law, which is used for magnetic braking. In general, these conducting loops will try to resist the change in flux. So not to resist the flux, that is to resist the change in flux. By producing these currents that interact with the B field. And so your moving conductor will experience this force that is like a drag force is opposing and slowing it down. As we see earlier in the when we were doing a loop that's leaving the field, right? Your force is opposing the direction where you're going. We can also use an application when you do these vending machines. And how would your vending machine know which coin do you throw in? Is it a quarter? Is it a dime? And it's also using the idea of the Faraday's law is that when your coins are rolling around, right? It will pass these magnetic field. So as it rolls around, you have a magnetic field on the way. And it will generate some eddy currents in the coin, just like how we did see in the magnetic braking demo. So depend on how much, what kind of material you're looking at, the size of the coin, it can detect, okay, you have given me a dime, spits it out. It's not the coin I'm looking for. It will be able to tell you what kind of coin you throw into the machine. So it's also an application of Faraday's law. Another very important, interesting point is magnetic force doesn't do work on particles. We have talked about this in the very beginning when we do QV cross B, right? You can see this force is perpendicular to the V, and when we do force work is F dot into DL, right? And DL is the V in the same direction as your at the path you're taking is in the same direction as your V. So if F is perpendicular to V and DL is the same direction, is the dot product is going to be 0. Magnetic force doesn't do work on individual particles. So we have already established that. But obviously you can see by slowing things down, the magnetic force can do work in general on these objects. Is there a paradox? So you can read upon in your textbook, and also there is an article that explains a little bit more about why there is a difference between these two. They're also worked on by magnetic force. So read a little bit about that. But it turned out has to do with, if we're looking at this metal bar, the little microscopic charges inside the metal bar, the charges moving relative to the bar is like this velocity going down. But at the same time, the entire bar is moving to the right with the velocity going to the right. So if you're looking at these charges, it looks like it has these two components. The overall velocity of the charge is actually in this direction, right? So you need to, when you're looking at the magnetic force done on individual particles, you're looking at a totally different path if you're looking at a force done by the metal bar overall. Of course, magnetic force can do overall work on these current carrying wires or these metal bars, but it doesn't do work on these individual charges because you can see there are two different components going on. The force can do work. This one will do work. This one will do work. But if you're looking at the overall velocity of the individual charges, and the magnetic force doesn't do work. Okay, so differentiate from when we are talking about work done on macroscopic objects. So these two are different things, and they do not have a conflict with each other. On the topic of Lenz's laws, let's look at a few more examples on the Lenz's law application. Okay. All right. So here we're going to produce, we're going to really focus on what does it mean to fight the change? What is a negative sign? Okay, so we have a loop of wire, the current pointing to the right, but it's decreasing. And you put a loop right next to it. Inside loops, are you going to have some generated induced current? And if so, in which direction is your induced current? Okay, so I'm going to let you go ahead and discuss this for a few minutes, and then we can vote. Noticing that there is no B field, right? But the B field is generated by your current. And you have to think about, okay, in which way is my B field pointing at for the location of the loop? All right, we'll run the clock for 10 more seconds. Okay, I'm going to go ahead and end the poll. All right, so which way would you think the induced current will be? So first of all, let's figure out the direction of the B field. In which way do you think the B field is pointing at the location of the loop?
Into the page.
Into the page. Very good. So we use the right-hand rule. Your current pointing to the right, your B field curling around at the location of where your loop is, B is into the page. Okay, so this B field that's into the page is now decreasing. So because current is decreasing, so B is also decreasing. Okay, B is decreasing. To fight that change, the loop want to produce an induced current that give us a B field, an induced B field, in which direction?
In the opposite direction.
To fight the change, not to fight the B field. Now, if B is decreasing, we want to produce E that's opposing that direction, but B is decreasing. So what would be opposing that change? Is to produce a B that is in the same direction or in the opposite direction.
Wouldn't it be the same direction?
It will be producing a B in the same direction as your B before, because that is fighting the change, not the B field, but the change. Okay, so you wanted to produce this B. It's like when the B is going, is leaving, and you're fighting that change. Don't go, and produce the same B. But if B is increasing, then you want to oppose it by producing a B that is in opposite direction. So whatever it is, it's going to fight just the change. So you can see that following that, following that into the page, give you a induced current that is in the clockwise direction. Okay, is correct. And that negative sign is reflected in the minus sign here in both places.
Chơi hứng thú là
Okay, so further, let's look at more of Faraday's law and answer more questions related to Faraday's law. So here we have a question: a long solenoid, which has a cross-section area A and has created a magnetic field B. So B is spatially uniform inside and zero outside of the solenoid. So we want to be able to find the electric field inside. We're going to use Faraday's law to help us understand this question. So how do we go about doing this? So how can you further expand upon this equation? Which one of these would be a correct expand upon this equation? How do we calculate B? Okay, so I'm going to let you go ahead and discuss this before we come back to vote on this. Okay, 10 more seconds, and then we're going to look at this together. All right, any last minute vote? All right, let's take a look. So this is using Faraday's law to calculate the induced E field, So we're using the integral format to calculate E. And let's see how do we expand the left-hand side and the right-hand side, okay? So the left-hand side, because your B is, you can see that when we have something like this, right? Your B and J are perpendicular. When J is directly upward, your B is curling around. In this case, our E and B are in such a relationship, right? The curl of E gives you B. So when B is pointing directly up, then your E is curling around. So we know that we should choose a loop that is in the same directions as our B. So to calculate B, you probably will do a loop inside that is like a circle, right? So you do E times 2 pi r of the circle, the circumference of the circle is your left-hand side. And your right-hand side would be, the flux is B times A. Area is not changing. It is a B that is changing. So it is dB over dt. Right, so this becomes this. And you can see E would be negative A dB over dt, 1 over 2 pi r. So the answer would be D, right? Okay, so we will do more examples on Faraday's law and calculate the EMF, and we will have at the end of this class a complete picture for Maxwell equations. That all of these equations will become a time-dependent case. Right, so we had curl of B dB over dt. The last one is, sorry, not this one. mu naught J.
Professor, can you scroll down a little bit?
Sorry.
Okay, thank you.
So we did the time dependence in this case. So we'll do more example next time, and also we will modify this equation to have a time dependence in it, okay? And then after that, we will have a full set of Maxwell equations that's depend on time. Okay, I want to let you know that I've uploaded the solution to your practice final exam. Make sure you have a chance to solve it on your own before you look at the solutions. And if you have any questions, welcome to see me. If I don't see you at office hours, I will see you guys on Friday in our recitation, okay? All right, guys, have a nice day. See you guys.
Thank you, Professor. You too.
Thank you.
Thank you, Dr. Ryan.
Thank you, bye-bye.